In this experiment, we investigate the properties of forced convection heat transfer. Natural convection differs from forced convection in that there is no external source of airflow, such as that from a fan, pump, or wind. Flow is achieved instead from the heat itself. As thermal energy moves to the air in contact with heat source, its density is decreased. Since it is now lighter than the air which it surrounds it, it experiences a buoyancy force which drives it upwards. And cooler, denser air fills in behind it, and the cycle repeats. Determining the velocity that is generated in the air by the heat is very difficult using only analytical methods. Due to this complexity, we decided to use a forced convection setup for the experiment. The experiment was conducted in the vicinity of a fan which provided the cooling air to the pan. The main goal of this experiment was to obtain a theoretical value for the time that the pan would need to cool, using methods from our coursework and textbook, and compare them to actual experimental values to determine the validity of our findings. The pan, while symmetrical, is a complex shape, and we anticipated a gap between our experimental and analytical findings, due to some basic assumptions that we would need to make in order to be able to manually calculate the time value using the equations available to us. For our experiment, we set the pan up vertically in a vise, heated it with the oxyacetylene torch, making sure to spread the heat evenly across the surface. The area where the pan was set up was in the cross flow of a fan some distance away. We then measured the time that it took to reach different temperatures as it cooled. We will compare the time that it took to cool to a calculated theoretical value. In order to do this, we will be making a few assumptions. Due to the fact that the cast iron has a much higher coefficient of heat transfer than air, it is assumed that the temperature of the pan is a uniform throughout. Mathematically, this is verified by the Biot number. We also assume that due to the size of the lab space, the net charge and air temperature will be negligible. We also treat the pan one dimension due to the difficulty of 2- and 3-dimensional analysis and the symmetry of the object. In addition, in calculating the surface area, the sides are treated as straight when in fact they are beveled out, as a difference due to this should be negligible, and it is determined as follows. We set the pan in a vise in the mechanical engineering lab and began to heat it at various locations across the back surface. We allowed a small amount of the time for the heat to dispense throughout the pan and then began to measure the temperature at various times. The rate at which the pan was cooling eventually slowed, and as it became close to room temperature, we took one final reading of the temperature and time. With some rearranging and realizing that density and volume combine to form mass, we obtain the measured pan that we have the temperature measurements from the experimental data that we will use here also. The specific heat of iron at the average temperature was found, and the surface area of the pan was already calculated. In order to find the convection coefficient, the velocity of the air provided by the fan was estimated. Our first step in this process is to determine the properties of air as the mean temperature. We can use them as the kinematic viscosity to find the Reynolds number associated with that velocity over the pan. This Reynolds number, in turn, can be used to find the average Nusselt number, given that it is laminar flow over a plate. The last step is to find the coefficient H is using in its relation to the average Nusselt number as follows. Our calculated value isn't too far off from our measured time of 1,515 seconds. The error between the two could be from any of the numerous assumptions that we made. In fact, it is genuinely surprising how similar the two values are to each other. It is a very good idea that things as complex as this is to obtain an actual experimental data.